Good day everyone. In this video, we are going to tackle the steam power cycles. In a steam power cycle, the working fluid is alternatively vaporized and condensed. Steam is the most commonly employed working fluid in steam power cycles due to its numerous beneficial features such as low cost, availability, and high enthalpy of vaporization. Rankine cycle is the ideal cycle for steam power cycles. With that, steam power plant operates in Rankine cycle and its modification. To increase the efficiency of steam power cycles, there are things that we can do. These include increasing boiler pressure, superheating steam before entering the turbine, and lowering condenser pressure. So for the ideal Rankine cycle, this is the schematic diagram of ideal Rankine cycle, and this is the TS diagram of ideal Rankine cycle. For the processes, at point 1 to point 2, there is an isentropic compression in a pump. In point 2 to point 3, there is a constant pressure heat addition in a boiler. And at point 3 to point 4, the isentropic expansion in a turbine. And point 4 to point 1, constant pressure heat rejection in a condenser. Let's go to the energy analysis of the ideal Rankine cycle. For the pump, the work needed to operate the water pump is work pumped in equals the difference of the enthalpy between the point 2 and point 1. Work pumped in could also be solved by using the specific volume at point 1 times the difference between the pressure at point 2 and point 1, where H1 equals HF at point 1 and V1 equals VF at point 1. In the boiler, the amount of heat supplied in the steam boiler can be calculated by Qn equals H3 minus H2. For the turbine, the amount of work produced by the turbine can be solved by H3 minus H4. For the condenser, the amount of heat rejected to cooling medium in the condenser is equals to Q out equals H4 minus H1. And to get the thermal efficiency equals work net over Q in, or equals to 1 minus Q out over Q in. In an actual vapor power cycles, there are irreversibilities. No steam power plants operate in a 100% efficiency. That's why there are deviations of actual vapor power cycles from idealized ones. These irreversibilities come from fluid friction, heat loss, irreversibilities occurring within the pump and the turbine, or the non-isentropic compression and expansion. For the pump, this is the formula to get the efficiency. Ideal work over actual work can also be solved by H2S minus H1 over H2A minus H1. For the turbine, we can get the efficiency of the turbine by the work actual over work ideal equals H3 minus H4A over H3 minus H4S, where states 2A and 4A are the actual exit states of the pump and the turbine, respectively, and 2S and 4S are the corresponding states for the isentropic case. And for cavitation and others. With these irreversibilities, modifications of Rankine cycle are made. Some of them are the ideal reheat Rankine cycle and the ideal regenerative Rankine cycle. The ideal regenerative Rankine cycle comes in two types. The closed feed water heater, those use the closed feed water heater, and the open feed water heater. This is the schematic and TS diagram of ideal reheat Rankine cycle. So the ideal reheat Rankine cycle differs from the simple ideal Rankine cycle in that the expansion process takes place in two stages. As we can see, there are two turbines. In the first stage, the high pressure turbine, steam is expanded isentropically to an intermediate pressure and sent back to the boiler, where it is reheated at constant pressure, usually to the inlet temperature of the first turbine stage. Steam then expands isentropically in the second stage, or the low pressure turbine, to the condenser pressure. There are positive aspects of ideal reheat Rankine cycle. So it is a practical solution to the excessive moisture problem in turbines, and it is commonly used in modern steam power plants. The incorporation of the single reheat in a modern power plant improves the cycle efficiency by 4 to 5% by increasing the average temperature at which heat is transferred to the steam. Then, there are also negative aspects of ideal reheat Rankine cycle. These include the following. 1. The use of more than 2 reheat stages, however, is not practical since the theoretical improvement in efficiency from the second reheat is about half of that which results from a single reheat. 2. If the turbine inlet pressure is not high enough, double reheat would result in superheated exhaust. This is undesirable as it would cause the average temperature for heat rejection to increase and thus the cycle efficiency to decrease. And third, a third reheat stage would increase the cycle efficiency by about half of the improvement attained by the second reheat. This gain is too small to justify the added cost and complexity. Now let's go to the ideal regenerative Rankine cycle. So the ideal regenerative Rankine cycle, so it is a practical regeneration process in steam power plants is accomplished by extracting or bleeding steam from the turbine at various points. This steam, which could have produced more work by expanding further in the turbine, is used to heat the feed water instead. The device where the feed water is heated by regeneration is called a regenerator or a feed water heater. A feed water heater is basically a heat exchanger where heat is transferred from the steam to the feed water either by mixing the two fluid streams, also called open feed water heaters, or without mixing them, or closed feed water heaters. This is the ideal regenerative Rankine cycle. So the T is and schematic diagram of ideal regenerative Rankine cycle with an open feed water heater and the other one with a closed feed water heater. So let's discuss the positive aspects of ideal regenerative Rankine cycle. So number 1, regeneration improves cycle efficiency. Number 2, it provides a convenient means of deaerating the feed water. So it means removing the air that leaks in at the condenser to prevent corrosion in the boiler. The third, it also helps control the large volume flow rate of the steam at the final stages of the turbine due to the large specific volumes at low pressures. Therefore, regeneration has been used in all modern steam power plants since its introduction in the early 1920s. So let's compare the open and closed feed water heaters. For the open feed water heaters are simple and inexpensive and have good heat transfer characteristics. They bring the feed water to the saturation state. For each heater, however, a pump is required to handle the feed water. On the other hand, the closed feed water heaters are more complex because of the internal tubing network, and thus they are more expensive. Heat transfer in closed feed water heaters is also less effective since the two streams are not allowed to be in direct contact. However, closed feed water heaters do not require a separate pump for each heater since the extracted steam and the feed water can be at different pressures. Now, let's move on to the calculations. As instructed, we will design a steam power cycle that can achieve a cycle thermal efficiency of at least 40% under the conditions that all turbines have isentropic efficiencies of 85% and all pumps have isentropic efficiencies of 60%. So consider a steam power plant that operates on a simple ideal Rankine cycle. Steam enters the turbine inlet at 10 MPa and 600 degrees Celsius and leaves the condenser as a saturated liquid at a pressure of 2.6 kilopascal. The isentropic efficiency of the turbine is 85% and that of the pump is 60%. So this is our TS diagram for the simple ideal Rankine cycle of the given problem. So this is our first attempt. The given steam enters the turbine at 10 MPa and 600 degrees Celsius and the condenser pressure is equal to 2.6 kilopascal. There is a condition that the isentropic efficiency of the turbine is 85% and for the pump is 60%. At state 1, so the pressure is 2.6 kPa. It is a saturated liquid. Therefore, we get the enthalpy, the entropy, and the specific volume. For the state 2, the pressure is 10 MPa and entropy at point 2 is equal to the entropy at point 1. Then we get the H2S, so the ideal enthalpy at point 2. So we get 101.1883945 kilojoules per kilogram. Then we get the work of the pump in Act 1. So we can get it by multiplying the specific volume at point 1 with the difference of the pressure between at point 1 and at point 2 and at point 1 over the efficiency of the pump. Then we get the work of the pump in Act 1. This is the work. Then for pump efficiency of 60%, we can get the H2. So using this formula, H2S minus H1 over 0.6 plus H1, we can get the H2 107.8673242 kilojoules per kilogram. At state 3, the pressure is 10 MPa at 600 degrees Celsius. So the Tsat at 10 MPa is 311.06 degrees Celsius. Therefore, state 3 is superheated. Then at table 3 of the steam tables, we get the values for enthalpy and entropy. At state 4, pressure at point 4 is equals to pressure at point 1, which is 2.6 kilopascal. At this point, it is a saturated mixture. So S4 equals S3 equals 6.9029 kilojoules per kilogram. Okay. So we note that at 26 kilopascal, these are the values for enthalpy, for entropy. So since it is a saturated mixture, we get the quality. So using this formula, S4 minus SF over SFG, we can get the X4S, which is 0.7922338979. Then, using this quality, we can proceed to calculation to solve the H4S. This is the H4S. H4S. Then, using the turbine efficiency 0.85 in the formula, we can get the H4. This is the value for H4. Thus, using the data, we can get the Qin by the difference of H3 minus H3 and H2. So we get the Qin 3517.432676 kilojoules per kilogram. Then we can also get the Qout by subtracting H4 by H1. So we get the Qout 180.013932 kilojoules per kilogram. Then we can get the thermal efficiency using the formula 1 minus Qout over Qin times 100%, in which we get 38%. So using the second attempt, using the same given in the first problem, but raising the boiler pressure from 10 MPa to 15 MPa. So this is the diagram. So we use the same process in getting the thermal efficiency. So at this point, using the given in the first problem, then we only change the pressure from 10 MPa to 15 MPa. So temperature 600 degrees Celsius, then condenser pressure is 2.6 kPa, given that the isentropic efficiency of the pump is 60% and of the turbine 85%. So we get the efficiency of 38.9198841%. So we use the third attempt, using the same given in the first problem, but raising the boiler pressure from 10 MPa to 15 MPa and increasing the boiler temperature from 600 degrees Celsius to 800 degrees Celsius. So this is the test diagram for simple ideal Rankine cycle of the given problem. So at pressure 15 MPa and at 800 degrees Celsius. So using the same process, we get the thermal efficiency of 41.5128047%. So we get the desired thermal efficiency. Then for the next, we consider the ideal reheat Rankine cycle. For the design information, consider a steam power plant that operates in a reheat Rankine cycle. Steam enters the high-pressure turbine at 10 MPa and 600 degrees Celsius, and the low-pressure turbine at 300 kPa. Steam leaves the condenser as a saturated liquid at a pressure of 2.6 kPa. The isentropic efficiency of the turbine is 85%, and that of the pump is 60%. So this is the diagram for ideal reheat Rankine cycle. So given steam at the high-pressure turbine, P equals 10 MPa, and temperature is 600 degrees Celsius. So pressure in the reheater, 300 kPa. Condenser pressure 2.6 kPa, and isentropic efficiency of the pump 60%, and for the turbine 85%. So at state 1, it is a saturated liquid at 2.6 kPa. These are the values of enthalpy, specific volume, and entropy. At state 2, pressure 2 is 10 MPa and S2 equals S1. So we can get the H2S, which is 101.1883945 kilojoules per kilogram. Then we can get the work of the pump in actual, which is 16.69732423 kilojoules per kilogram. So using the formula for pump efficiency of 60%, H2S minus H1 over H2 minus H1 equals 0.6, we can get H2 107.8673242 kilojoules per kilogram. At state 3, so pressure 3 equals 10 MPa at 600 degrees Celsius. So Tsat at 10 MPa is 311.06 degrees Celsius. So state 3 is superheated. So at state 4, P4 equals P5 equals 300 kilopascal. Then we get the S3 equals S4S. So this is the value. Then SG at 300 kPa is 6.9919. So since S4 is lesser than SG at 300 kPa, there is quality X4. So using this formula, X4 equals S4 minus SF over SFG, we can get the X4, which is 0.9832709911. So using this quality, we can get the H4S. This is the H4S. Then proceed using the turbine efficiency and the formula, we can get the value of the H4. This is the value of the H4. Then at state 5, pressure is 0.3 MPa and the temperature is 600 degrees Celsius. So at 0.3 MPa, Tsat equals 123.55 degrees Celsius. Thus, at 600 degrees Celsius, the steam is as superheated before. So at table 3, we can get the values of H5 and S5. At state 6, the pressure is 0.0026 MPa. And we can see that using the values of SG at 0.0026 MPa, there is a quality X6. So using this formula, we can get the value of X6. Then using the value of X6, we can get the values of H6S. This is the value of H6S. Then for turbine efficiency, using the formula, we can get the value of H6. This is the value. And we can proceed to get the Q in by the H3 minus H2 plus H5 minus H4. So we get the Q in of 4391.126671 kilojoules per kilogram. Then proceed to getting the Q out. H6 minus H1, we get 2614.412625 kilojoules per kilogram. Then we get the work net. Q in minus Q out equals 1776.714046 kilojoules per kilogram. So getting the work of the turbine out equals work of turbine 1 plus work of turbine 2 equals H3 minus H4 plus H5 minus H6. So we get 1793.41137 kilojoules per kilogram. Proceed to getting the thermal efficiency using the formula 1 minus Q out over Q in. We can get that the thermal efficiency is 40.46146,192%. So we get the desired design. Consider a steam power plant that operates on the ideal regenerative Rankine cycle with a closed feed water heater as shown in the figure. The plant maintains the turbine inlet at 10 MPa and 600 degrees Celsius and operates the condenser at 2.6 kPa. Steam is extracted at 300 kPa to serve the closed feed water heater, which discharges into the condenser after being throttled to condenser pressure. The isentropic efficiency of the turbine is 85%, and all pumps have isentropic efficiencies of 60%. So this is the TS diagram for ideal regenerative Rankine cycle. So the pressure, temperature, enthalpy, entropy, and specific volume are given, are written at every state. For the calculations, given steam at the high pressure turbine, pressure equals 10 megapascal at temperature 600 degrees Celsius. Then pressure in the feed water heater, pressure equals 300 kPa. Then condenser pressure is 2.6 kilopascal, given that the isentropic efficiencies of the pump is 60% and for the turbine 85%. At state 1, it is a saturated liquid, 2.6 kPa. So we get the temperature, enthalpy, specific volume, and entropy at state 1. At state 2, pressure is 10 megapascal, then S2 equals S1, which is 0.3211. So we calculate for the H2S, we get 101.1883945 kilojoules per kilogram. Then we get the work of the pump in actual. So we get 16.16732423 kilojoules per kilogram. Using the pump efficiency of 60%, we can get the H2, which is 107.8673242 kilojoules per kilogram. At state 4, pressure at state 4 is 10 megapascal, then temperature 600 degrees Celsius. We can get the values of H4 and S4. At state 5, the pressure is 0.3 megapascal. So at 0.3 megapascal, SG equals 6.9919 kilojoules per kilogram K. It is a mixture. So since it is a mixture, we will solve for the quality, X5S. So values at 0.3 MPa for SF and SFG. We can proceed to the calculation of X5S, which is 0.9832709911. Using the value of X5S, we can proceed to get the H5S. This is the value of H5S. And using the efficiency equals H4 minus H5 over H4 minus H5S, we can get the H5 to 829.5060005 kilojoules per kilogram. At state 6, pressure at state 6 equals to pressure of state 1, 26 kilopascal, 2.6 kilopascal, or 0.0026 megapascal. Then S6 is equals S4 equals 6.9029 kilojoules per kilogram K. And since SG at 0.0026 megapascal equals 8.629 kilojoules per kilogram K, So since A6 is lesser than SG at 0.0026 megapascal, there is equality. There is X6. So using this formula, we can get the value of X6 is, which is 0.7922338979. Using the value of the quality, we can proceed to get the value of H6S. This is the value of H6S. Then we use the turbine efficiency and the formula. This formula, we can get the value of H6, which is 2271.183932 kilojoules per kilogram. At state 7, the pressure is 0.3 megapascal, and the X7 is equals to 0. So means it is a saturated liquid. So H7 equals HF equals 561.47 kilojoules per kilogram. Then the temperature, Tsat, is equals to 133.55 degrees Celsius. So at state 3, P3 equals 10 megapascal. Then using the temperature at 0.7, the Tsat, T3 equals T7 equals 133.55 degrees Celsius. So at 10 megapascal, we'll look for the table 4 in the steam tables to solve the H3. So by interpolation, we can get that the value of H3 is 568.07845 kilojoules per kilogram, and the value of entropy at point 3 is 1.66137.825 kilojoules per kilogram. So we proceed to get the value of Y. Using the formula, Y equals H3 minus H2 over H5 minus H7 to get 0.20291117372. Then we proceed to get the value of the turbine out equals H4 minus H5 plus 1 minus Y, quantity 1 minus Y times quantity H5 minus H6. We get the work of the turbine out 1240.825966 kilojoules per kilogram, and the work of the pump given we have computed earlier 16.69732423 kilojoules per kilogram. So we proceed to get the Q in using the formula H4 minus H3. Q in equals 3057.22155 kilojoules per kilogram. Then we proceed to get the work net. Work net equals work of the turbine out minus work of the pump in equals 1224.128642 kilojoules per kilogram. Then we proceed to get the thermal efficiency. So using the formula, thermal efficiency equals 1 minus Q out over Q in, or equals to work net over Q in. So times 100%, we get the thermal efficiency of 40.04056042%. So it meet the desired output or the design. So that's all. Thank you so much.